March 8th, 2018. Well, here we are. So I was going to carry forward and put some cooler setups, cooler fans on the CPU, on the Pi, and on the box. I've gone ahead and done that. And I have them set right now. The main CPU cooler fan right there to come on at 100 degrees, and the box fan to come on at 101. Mostly just so they would trip on, and I could see that they were actually working correctly. Now that they're set correctly, I'll probably set the top one at, say, 140 or even 150, and this one at, say, probably 155 or 160, and that way when summertime temperatures start climbing, we'll be able to keep things cool. The airflow in here is pretty incredible. I'm pretty impressed. And I looked up before and realized that even with both the fans going, the Pi going, the circulator pump for the hydronic system, because we have a lot of heat in the thermal mass on top of the stove, right there, all those running, it was still only about 16 watts. So that's not bad at all. And of course in the summertime, when these will be running mostly, there'll be plenty of sunshine and day length to compensate for that power usage. So I guess we'll just give you a shot here of the screen, of the monitor. You can see the CPU temp is currently 107.6. Let's see, when we booted back up, before the fans came on, before the fans came on, you can see it was around 120, 113, 113, and then when the fans came on, it dropped to 109 to 111, and now we're down to 107 with the box door open. Interesting. You can see that the relays are lit up. The bottom two relays are the CPU fans. This is the main CPU cooler fan. This is the box cooler fan. And then of course the third relay is the start of the hydronic and air circulation fan relay array for the greenhouse. I currently have this monitor running. This is a monitor my friend Dave gave me. Thank you, Dave. Happy birthday, by the way. This is excellent, perfect size for a temporary setup, at least for the greenhouse. Ultimately, without having to drill some big holes in the bottom of the box here to bring the VGA connector through, that's not going to work. But I am set up with an HDMI connector. Eventually I'll probably get a 12 volt smaller, probably like a 10-inch or so monitor to go up here, so everything's independent. I think I found one on Amazon. They say it draws like 8 watts or something. That's a nice low power consumption. But anyway, in the meantime, that's running on the power inverter and plugged into the system. So you'll see, even with the monitor, the power inverter, both fans, the Raspberry Pi, and the hydronic circulation system on, we're still only drawing about 32 watts. And so just to show you what the total power consumption is, we'll take the monitor out of the equation. Sorry for the camera unsteadiness. Ready? Monitor off. Yeah, we're under 16 watts. We're 15.48 watts. And that's running both of those fans and the hydronic circulator pump over here, which is circulating and taking heat out of the top thermal mass and putting it down into the secondary thermal mass. Again, that's just for testing right now. Eventually we'll change that out and put in a larger thermal mass reservoir that'll probably go on the north end of the greenhouse here, like I said, where these barrels are. And according to my calculations, if I go with a 2-foot high tank, 4-foot wide, 12-foot long, that'll give me about 718 gallons, which is about 2.7 times the volume of water I have here in these 3 thermal masses all together. And that'll give me plenty of headroom for long overnights. I'll be able to exchange that heat into the bank and store it. And I think I'll probably build that bank out of a wooden frame and EPDM liner. If you're not familiar with EPDM liner, it's rated up to 300 degrees operating temperature. It's fairly cheap, and it's an easy way to make a tank or pool. So that's probably what I'll do, with some sort of a some sort of a deck on top of it, and then I'll have planting space in here. I won't lose the planting space to barrels and that sort of thing. So that'll make this whole system much more efficient. Along with that, if I can afford it and I have the time to put it together, I probably will replace the wood stove with some sort of a rocket furnace or something that'll also be controlled by the Pi, and we'll do away with producing a lot of direct heat in this space, and we'll basically water jacket that entire furnace and capture that heat directly to the water jacket. I probably will make that use a passive exchange with thermosiphon, where the hot water rising will actually exchange the heat back to the big tank, and then we'll just use the circulator pump when we want to defrost stuff, or you know, heat specific beds or areas, or defrost the chicken coop, that sort of thing. But we'll see how that works out. That's expense, time, design work, etc. But that is an ultimate next step that I'd like to take to make this whole system more efficient. And of course, once that large tank was in there as basically a shelf, that would clear out these other two tanks and make a lot more room in the greenhouse. And with the water jacketed system, you won't have that radiant heat area that you have to stay away from the stove. In other words, even this poor lemon tree here, actually the side of this pot gets quite warm when the stove runs hot, and so that's kind of an issue where you basically lose a tremendous amount of space to the stove, where if it was water jacketed, it wouldn't radiate that much heat, and we'd be much more efficient in capturing that heat and storing it for later. So I hope this has been informative and interesting for you. There's a couple of links I found on Raspberry Pis overheating and burning up. Some conflicting results in there, but I figured I'd take the precaution and prevent any meltdowns or fried processors. I don't need that, especially in the summertime when it would be most likely to happen in the middle of a busy growing season. So I hope this has been informative, and hope that you'll like, subscribe, or comment if it's appropriate. If you're not into this and you know someone who is, please pass it along to them, or someone who might find it interesting. Thanks again for watching the Pharmacy Seeds Network. A couple other quick details I meant to point out. I've also added a output temperature sensor on the coil, so I can see when the coil is running and what the temperature of the water coming out is, and I can actually see what the difference between the temperature in the thermal mass and the water coming out is. Very handy for calculations, and later on for adjusting algorithms and codes for more efficient transfer of heat. The other thing I wanted to point out was I added another sensor in the box here. It's just a DS18V20 mounted right in front of the CPU cooling fan. This way we actually have air temperature inside the box, both for the database for data logging, and I've modified the code now so that the exhaust fan only comes on when the box reaches a certain temperature. I think I have it set at 100 degrees now or something like that. But that way the two fans operate independently. So far in the winter here, the box has been running around 75 to 78 degrees, in that range, and we'll see as summer comes on, the box temperature will start coming up. I'm sure this fan will start kicking on and exhausting. I did test it. I used a soldering iron to heat the sensor up enough to make it trip the fan on. It does work, and yeah. So just a couple other little details I wanted to point out. Thanks for watching the Pharmacy Seeds Network. March 11th or 12th, 2018. Perfect timing. The fans just came on. That one and that one. And you can see the relay fired. Relay number 4 going from the bottom to the top. You can see the pump relay is also on. The thermal mass is pumping heat. Lots of heat. Maybe I'll snag a screenshot of that. Anyway, for now we're just comparing the two sensors, west high, that sensor, and east high with the corresponding sensor on the other side. If the difference is greater than 5 degrees, we kick the fans on, both of them, to blow the warm air over that way. Eventually I'll complicate this algorithm with high and low temperatures, outside temperatures, all sorts of other input data. Oh, and now it just went back off. But I just wanted to show proof of concept for air movement. A side note, I was looking at DC fans to run in here for moving the plants around to help build stem strength, because you want to keep stems moving, because that breaks their cells down and makes them grow back, a lot like us doing exercise, breaking our muscles down and growing back. I looked at this fan, which produces a tremendous amount of air, but it's also really noisy and loud, and it's a really annoying frequency, really annoying tone. So, just for giggles, I decided to run this fan off the inverter and see how many watts it takes, and it's 36 watts. So I figure if I run that 1 minute for every 5 minutes, then I'm running 20% duty cycle, then basically for 7 watts an hour I can bring that on and disturb the plants and do the airflow that needs to be done and not burn a lot of power to do it. So I'm looking at incorporating some sort of inverter. I may use this uninterruptible power supply as my inverter source, but I gotta tear it down and have a look and see if it's really as applicable for that as I want. That said, the small inverter will run this, so I may just temporarily rig that up with a power strip and run it through a relay so it will have its own relay, but we'll look at that. Anyway, I mostly just wanted to show the fans on the upgrades. I think I went over all the other stuff in the other pieces of this video. Thanks for watching the Pharmacy Seeds Network.